When a massive enterprise application faces the stress of real-world traffic, the underlying infrastructure absorbs the full impact. Designing these systems has evolved beyond the subjective craftsmanship of writing code. It is a rigorous engineering discipline. Operating with qualitative goals, telling an engineering team to make the platform fast or ensure it is reliable, guarantees failure. You cannot mathematically measure fast when a system is processing 1 million concurrent requests. You cannot rigorously test reliable in a staging environment. And you cannot write a contract guaranteeing a subjective feeling to an enterprise client. Without strict quantification, the architecture inevitably collapses under the weight of undefined operational expectations. Building software at scale requires moving away from simply coding isolated features. The focus has to shift toward designing holistically governed systems. To do that, engineering teams replace vague objectives with architecturally significant requirements, or ASRs. An ASR is any system requirement that carries exceptionally high business value and dictates the primary structural design choices of the application. If the architecture cannot support one of these requirements, the entire system has to be torn down and rebuilt. They are architecture killers. To satisfy an ASR, the engineering team must discard subjective language entirely and implement a mathematically rigorous reliability stack. The base of this reliability stack relies on raw continuous measurement, taken strictly from the user's perspective. This measurement is called the Service Level Indicator, or SLI. An SLI is not a basic server health check. It does not ask a generic question like, is the database running? Instead, it tracks the exact proportion of HTTP requests served within a specific millisecond threshold. This graph shows the base quantitative metric for system behavior, plotting hundreds of individual user requests across a timeline. SLIs strip away developer bias. They prove mathematically exactly what the end user is experiencing in real time. But raw SLI telemetry gives you no actionable direction without a defined threshold for acceptable internal performance. This requires a service-level objective, or SLO, which binds that raw SLI data to a specific success percentage over a rolling time window. On our chart, a yellow threshold line represents an internal SLO of 99.9% success. Above this sits the Service Level Agreement, or SLA, the legally binding external contract. Breaching this upper threshold triggers severe financial penalties and mandatory service credits. Site reliability engineers configure internal SLOs to be strictly tighter than external SLAs. This intentional gap triggers internal alerts, so the team can fix the issue before a legal breach occurs. This tiered measurement hierarchy takes subjective business desires and translates them directly into automated, enforceable architectural boundaries. When an entire enterprise system is prevented from receiving any updates, it is effectively freezing into solid ice. A prevailing engineering misconception is that systems should be designed for 100% reliability. In distributed environments, that is a mathematical impossibility. Chasing absolute perfection is financially prohibitive, and it actively harms the enterprise by halting all new feature innovation. The required architectural shift involves treating failure as an acceptable, quantifiable metric. This diagram displays the mathematical inverse of the SLO, an ultimate control mechanism known as the error budget. The reality of this equation is that a 99.9% reliability target strictly permits roughly 43 minutes of acceptable system downtime per month. In modern architecture, downtime is no longer an emergency to be avoided at all costs. Instead, it is a finite, spendable currency. The error budget serves as an objective governance bridge between the development team and IT operations. The core operational rule is simple. When the error budget is healthy, developers are explicitly authorized to push new features and take deployment risks. This visualization illustrates the burn rate, showing how aggressive feature deployments actively consume this finite resource over the course of a month. But there is an absolute architectural constraint. When the burn rate exceeds sustainability and the error budget hits zero, a structural lock engages. Firmly, this lock mandates an immediate, non-negotiable halt to all new feature rollouts. All engineering resources are forcibly pivoted entirely to system stabilization and technical debt reduction. Software architecture is not a static blueprint. It is a continuous, mathematically governed negotiation between feature velocity and structural integrity.